This video takes a closer look at the fundamentals of tolerancing components. The drawing shown depicts a plate with two holes. The dimensions indicated in the drawing are referred to as nominal dimensions. However, due to inaccuracies during the manufacturing of the component, there will later be more or less significant deviations from these nominal dimensions. For example, the short edge of the base plate is not exactly 70 mm long, but only 69.84 mm. Or the hole has a diameter of 20.10 mm instead of the specified 20 mm. The deviations between the theoretical nominal dimensions and the actual dimensions present later are due to the manufacturing process. For example, play in the guideway of the machine table or the machine tool can lead to inaccuracies. Play in the tool spindle can also result in the manufacturing process not being precise enough. In addition, deformation of the spindle can cause the tool to run out of round, negatively affecting dimensional accuracy. Furthermore, both the tool and the workpiece can deform during machining, which prevents precise manufacturing. Thermal influences must also be taken into account, as they can lead to deformation due to thermal expansion. Wear of the tool over time also prevents accurate adherence to nominal dimensions. For these reasons, a certain deviation between the nominal dimensions and the actual dimensions present later must always be accepted. However, this must not result in the functionality of the component being impaired. For example, if the base plate is later intended to slide in a guide rail, care must be taken to ensure that the deviation is neither too large nor too small. Otherwise, the plate might start vibrating while sliding if it is too narrow, or it might not fit into the rail at all if it is too wide. The designer must therefore indicate in the drawing which deviations from the specified nominal dimension are still permissible. These permissible deviations are called tolerances. Tolerances should not be chosen too small by the designer, as this would require more precise machine tools, more accurate measuring instruments, and therefore longer production times, resulting in higher manufacturing costs. This leads to the principle of tolerancing. Tolerances should be as large as possible without compromising functional reliability. In the drawing, various options for specifying tolerances are shown in red. These will now be explained in more detail. There are three types of tolerance specifications: direct tolerance specification, general tolerances, and the so-called isotolerances. First, let's take a closer look at the direct tolerance specification using the example of a nominal dimension of 100 mm, and explain the most important basic terms. In direct tolerance specification, the permissible deviations are written directly after the nominal dimension. These permissible deviations are called limit deviations, or simply deviations. Deviations can be either positive or negative. If the permissible limit dimension is larger than the nominal size, the deviation is positive. If the permissible limit dimension is smaller than the nominal dimension, the deviation is negative. Graphically, the larger of the two values is always placed above the smaller one. So keep in mind, deviations have a sign that indicates in which direction the dimension is allowed to deviate from the nominal size. The nominal size is symbolically represented by the capital letter N. In this case, the nominal size is 100 mm. The upper deviation is represented by the letter combination ES. These letters stand for the initials of the corresponding French words, which in English mean upper deviation. In our case, the upper deviation ES is plus 0.2 mm. The lower deviation is indicated by the lowercase letter combination EI. These letters correspond to the French words meaning lower deviation. In our case, the lower deviation EI is minus 0.1 mm. In general notation, a distinction is often made between outer and inner dimensions. Outer dimensions are usually referred to as shafts, while inner dimensions are referred to as holes. The deviations for outer dimensions are assigned lowercase letters, and those for inner dimensions are assigned uppercase letters. This convention will play an important role later in the context of isotolerances. Let us return to our example. Based on the given deviations, we can now determine both the permissible maximum size and the permissible minimum size, within which the actual measured value must fall. For both the maximum and minimum size, the corresponding value results from the sum of the nominal size and the deviation with its sign. The maximum size is represented by the letter combination Smax and is, in our case, the sum of the nominal size of 100 mm and the upper deviation of 0.2 mm. This results in a maximum size of 100.2 mm, which must not be exceeded after manufacturing. The minimum size is represented by the letter combination S-min and is the sum of the nominal size of 100 mm and the lower deviation of minus 0.1 mm. Here, it is important to pay attention to the sign. This results in a minimum size of 99.9 mm, which must not be undershot after manufacturing. The difference between the limit sizes defines the range within which the actual measured value may vary. This range is called the dimensional tolerance, or simply tolerance, and is symbolized by the capital letter T. In our case, the difference between the maximum size and the minimum size results in a tolerance of 0.3 mm. The dimensional tolerance can also be calculated by subtracting the lower deviation from the upper deviation. Here it is important to remember that subtracting a negative number, as in the case of the lower deviation, is mathematically the same as addition. This means we again get a tolerance of 0.3 mm. It is important to note that the dimensional tolerance is always a positive value, because the maximum size, or the upper deviation, is always greater than the minimum size, or the lower deviation, which ensures a positive result when calculating the difference. There is a special case when the allowed deviation is the same above and below the nominal size. For example, the distance between the centers of the holes may deviate by 0.1 mm above and below the nominal value of 40 mm. In such cases, where the tolerance range is symmetrical to the nominal size, a plus-minus sign is placed in front of the deviation. In this example, the maximum size of the distance between the hole centers is 40.1 mm, and the minimum size is 39.9 mm. The dimensional tolerance for symmetrical deviations is always twice the value of the individual deviation. In our case, this results in a total tolerance of 0.2 mm. Another special case in the specification of deviations occurs when an allowed limit size is exactly equal to the nominal size. This corresponds to a deviation of 0. In such cases, the deviation of 0 is usually not written down. This can be seen, for example, in the width of the base plate. There, only the lower deviation of minus 0.1 mm is specified. If only one deviation is given, the other deviation is automatically 0. This means that the upper deviation is 0 mm, and the lower deviation is minus 0.1 mm. The maximum size is therefore the same as the nominal size, which is 70.0 mm. The minimum size is 69.9 mm. If only one deviation is specified, that value directly corresponds to the tolerance. In this case, the dimensional tolerance is 0.1 mm. It is important to note that the upper deviation does not always have to be positive, and the lower deviation does not always have to be negative. Both the upper and the lower deviation can be either positive or negative. Let us take the example of the rail in which the base plate is later meant to slide. To ensure that the plate fits into the rail, the width of the rail must always be greater than the maximum size of the base plate. Only then can we be sure that the plate will fit into the guide rail. We could therefore specify an upper deviation of plus 0.2 and a lower deviation of plus 0.1 mm for the width of the rail. In this case, both deviations are positive. The maximum size of the rail width is then 70.2 mm, and the minimum size is 70.1 mm. Even in the worst case, where the rail is manufactured to its minimum size of 70.1 mm and the base plate to its maximum size of 70.0 mm, it is still guaranteed that the base plate will fit into the rail. In theory, it would also be possible to dimension the rail width with a nominal size of 70.1 mm and tolerate it with only an upper deviation of plus 0.1 mm. The lower deviation would then be 0. This would result in the same maximum dimension of 70.2 mm and the same minimum dimension of 70.1 mm. In practice, however, this is not done, because geometries that are intended to be joined later, such as in our case, the width of the base plate and the width of the rail, are always assigned the same nominal size. This makes it easier to match components later on based on the dimensions provided in the drawings. This becomes especially important later when working with so-called isotolerances. So note, geometries that are to be joined later are always assigned the same nominal size. In addition to the direct specification of deviations, there is another way to define tolerances. Wherever tolerances are not specified directly, for example for a nominal size of 25 mm, so-called general tolerances apply. The German supplementary standard DIN 2769, for example, distinguishes 4 tolerance classes based on the required level of precision. These are designated by the lowercase letters A, B, C, and D. The letter A stands for very fine tolerances, B for medium, C for coarse, and D for very coarse tolerances. The table shown lists the corresponding deviations for the different tolerance classes across various nominal size ranges. The deviations of general tolerances are always symmetrical to the nominal size. The nominal sizes are divided into different ranges, within which the same deviations apply. As the nominal size increases, the allowable deviations also increase. A nominal size of, for example, 20 mm has smaller deviations of plus minus 0.2 mm in tolerance class B than a nominal size of 100 mm, for which a tolerance range of plus minus 0.3 mm applies. The designer determines which tolerance class applies to the specific component and indicates this in the drawing outside the title block. In our case, tolerance class B applies. Let us consider the horizontal edge distance of the first hole center with a nominal size of 25 mm as an example. Since no direct tolerance specification is given in this case, a general tolerance with tolerance class B applies. According to the table, the nominal size range over 6 to 30 mm applies here. In the row for tolerance class B, we find a deviation of plus minus 0.2 mm. Thus, the maximum size is 25.2 and the minimum size is 24.8 mm, resulting in a corresponding dimensional tolerance of 0.4 mm. As a further example, consider the vertical edge distance of the hole centers with a nominal size of 30 mm. The question is now in which nominal size range we find the corresponding deviations. Should we look in the range over 6 to 30 mm or in the range over 30 to 120 mm? In case of doubt, it is generally advisable to choose the smaller deviations, as this automatically ensures that the larger deviations are also met. In fact, this is also the correct decision. The reason for this, upon closer interpretation, is the specification that the nominal size range over 30 to 120 mm only applies if the nominal size is actually over 30 mm. If the nominal size is exactly 30 mm, it is not over 30 mm. Therefore, the range that includes nominal sizes up to and including 30 mm actually applies. The limit deviations for the nominal size of 30 mm in our case are thus plus minus 0.2 mm. It should be noted that general tolerances exist not only for linear dimensions, that is for length measurements, but also for angular dimensions and for the form and position of geometries. However, we will not go into these in detail in this video. In addition to the direct specification of dimensions and general tolerances, there is another method of tolerancing. This is demonstrated by the hole diameter of 20 mm with the tolerance designation H7. This is a so-called isotolerance, which consists of a combination of a letter and a number. Together, these form the so-called tolerance grade. The letter defines the fundamental deviation, while the number indicates the fundamental tolerance grade. We will explain this in more detail shortly. At this point, the already mentioned convention applies that for the tolerancing of internal geometries such as holes or slots, uppercase letters are used to indicate the fundamental deviation. For external geometries such as shafts, lowercase letters are used. The example shown illustrates the diameter specification of a pin with a nominal size of 20 mm and tolerance grade G6. This pin is intended to be inserted later into the hole of the base plate. Let us first take a closer look at the fundamental tolerance grades, represented by the numbers within the tolerance grade designation. In the ISO system, a total of 18 fundamental tolerance grades are distinguished. These are labeled IT1, IT2, and so on up to IT18. The fundamental tolerance grades specify the dimensional tolerance depending on the nominal size. In the table shown, the respective dimensional tolerances are listed for nominal sizes up to 250 mm in various nominal size ranges for each fundamental tolerance grade. The dimensional tolerance resulting from the fundamental tolerance grade and the specific nominal size is also referred to as the fundamental tolerance. It is therefore important to distinguish between the term fundamental tolerance grade, which corresponds to the IT number, and the term fundamental tolerance, which is the actual specific dimensional tolerance. As a general rule, the higher the fundamental tolerance grade for a given nominal size, the larger the dimensional tolerance. The fundamental tolerance grades IT1 to IT4, highlighted in red, cover very tight tolerances, such as those required for the production of components for measuring instruments. Tolerance grades up to IT4 can only be achieved with complex manufacturing processes such as lapping, honing, or fine grinding. The fundamental tolerance grades IT5 to IT11, highlighted in blue, cover medium tolerances, which are used for components in conventional mechanical engineering. These tolerance grades can be achieved with common manufacturing processes such as turning, milling, reaming, and grinding. It should be noted that drilling alone is generally not sufficient to achieve tolerance grades between IT5 and IT10, but only in combination with subsequent reaming. Larger tolerances are found in the fundamental tolerance grades IT12 to IT18, highlighted in green. These are used, for example, for forged and stamped parts. Manufacturing processes such as rolling, forging, and casting usually allow only tolerances larger than IT12 to be realized. Let us consider as an example the previously explained pin with a nominal size of 20 mm, which is to be manufactured with the tolerance grade G6 and later joined with the base plate. First, it must be determined which dimensional tolerance is to be maintained. For this, we look in the table shown in the nominal size range between 18 and 30 mm. Then we move right in this row to the column for tolerance grade IT6. Thus, for our pin, we obtain a fundamental tolerance or required dimensional tolerance of 13 micrometers. Note that ISO tolerances are usually very small and therefore mostly given in micrometers. We now know that for our nominal size with tolerance grade IT6, a tolerance of 13 micrometers must be maintained. However, with this value alone, we cannot yet manufacture the pin in practice. Although we know the height of the tolerance zone, we do not know exactly where it is located. For example, the tolerance zone could lie with its upper deviation directly on the datum line of the nominal size. Then the pin would have to be manufactured between 19.987 and exactly 20 mm. But it could also be that the tolerance zone with the upper deviation lies below the nominal size, for example between 19.980 and 19.993 mm. This also corresponds to a tolerance zone of 13 micrometers. It is also possible that the dimension can lie between 19.996 and 20.009, thus slightly below as well as above the nominal size. It is also possible that the tolerance zone lies between 20.002 and 20.015 and is therefore entirely above the nominal size. In all the cases shown, the dimensional tolerance is always 13 micrometers. Therefore, the position of the tolerance zone is not yet determined by the indication of the fundamental tolerance grade alone. This is exactly where the fundamental deviation in the form of the letter given in the tolerance grade comes into play. This letter now precisely defines the position of the tolerance zone. This position, based on the letter, can be found in tables. In our case, for the fundamental deviation G, the tolerance zone shown on the far left applies. Consequently, the pin must be manufactured between the minimum size of 19.980 mm and the maximum size of 19.993 mm. We will explain how to read these values from the tables shortly. Let us first summarize the most important points about ISO tolerances. The tolerance grade consists of a letter and a number. The fundamental tolerance grade in the form of the IT number determines the size of the tolerance zone, while the fundamental deviation in the form of the letter indicates the position of the tolerance zone. At this point, it is worth noting an important fundamental deviation, namely the one with the letter H. This fundamental deviation H always places the tolerance zone exactly on the datum line of the nominal size and extends into the material. For shafts, this means they can be slightly smaller than the nominal size. For holes, this means they can be slightly larger than the nominal size. As already mentioned, the limit deviations for common ISO tolerances are given in the tables depending on the nominal size. Let us revisit our example of the pin. In this case, we first look for the corresponding row for our nominal size of 20 mm. This is located in the nominal size range between 18 and 24 mm. In this row, we then move to the right to the ISO tolerance grade G6 and can directly read the red-marked upper deviation of -7 micrometers and the blue-marked lower deviation of -20 micrometers. It is essential here to pay attention to the uppercase and lowercase letters. Lowercase letters are used for shafts and uppercase letters for holes. The table further distinguishes between the limit deviations of the so-called Series 1 and Series 2. ISO tolerance grades of Series 1 are preferred. If Series 1 is not sufficient, tolerance grades of Series 2 can also be used. Let us now consider our 20 mm hole with the ISO tolerance grade H7, into which the pin with tolerance grade G6 will later be fitted. The tolerance grade H7 in this case has a lower deviation of 0 and an upper deviation of 21 micrometers. In contrast to our pin, which with the fundamental deviation G is at least 7 micrometers smaller than the nominal size of 20 millimeters, the hole with the fundamental deviation H is therefore always larger than or, in the limiting case, equal to the nominal size. The upper part of the table also schematically shows the positions of the ISO tolerance grades listed in the table. It is also visually very clear here that if we combine the pin with the fundamental deviation G with a hole with the fundamental deviation H, the pin will always be smaller than the hole. Even if we manufacture the pin at the maximum size as shown, which corresponds to the largest possible diameter, and the hole at the minimum size as shown, which corresponds to the smallest possible diameter, the pin will easily fit into the hole. This is referred to as a clearance fit. If, on the other hand, the pin is manufactured with a tolerance grade R6, it will always be larger than the hole. Even if we manufacture the pin at the minimum size to make it as small as possible and the hole at the maximum size to make it as large as possible, the pin will not fit into the hole without force but must be pressed in with greater effort. This is referred to as a press fit or an interference fit. The pin could also be manufactured with a tolerance grade N6. In this case, the tolerance zones overlap. In one extreme case, if we manufacture the pin just at the minimum size and the hole at the maximum size, there will be clearance between the components. In the other extreme case, if we manufacture the pin at the maximum size and the hole at the minimum size, there will be interference. Since the exact actual dimensions are not known before manufacturing, this is called a transition fit. Here the advantage of ISO tolerances compared to other tolerances becomes apparent. They are standardized and are always used when two components are to be fitted together and a certain fit condition is to be achieved, such as the already mentioned clearance fit, interference fit, or transition fit. These fits and their underlying systems will be explained in more detail in another video. Let us briefly summarize the most important points about the tolerances we have learned. General tolerances can usually be achieved without significant manufacturing effort and are therefore preferred. If, for reasons of functional reliability, tighter or wider tolerances are required, these are specified by the designer as direct tolerance specifications. ISO tolerances generally require greater manufacturing effort and are used for fits, meaning the precise joining of two components.